Good morning, everyone. All right, so welcome to our first lecture on for CG2271. All right, my name is Mr. Ravi. Okay, most of you would have seen me either for EPP1 or EPP2. Okay, so half of your batch took 2271 last semester, and you are the second batch. I'm sure there are also other students who a bit more senior and who did not take this module earlier and then are taking it now. All right, so this first lecture, I'm going to brief you a bit on some of the important admin matters. Okay, how the module has changed tremendously over the last few years. Okay, and what you're up for, correct, in this current semester. Okay, so we have exactly 100 students registered for this module, and currently we have 83 of you here, which is a great number. Hopefully it stays as such throughout the semester. But anyway, all classes, all lectures will definitely be recorded and uploaded. For labs and tutorials, I will brief you all in a while. Okay, so let me share my screen. Okay, and then I'll get started with the first introductory lecture. Okay, so about me, like what I mentioned, my name is Mr. Ravi. Okay, this is my office, COM20336. I think most of the time I'm like 50-50. Half the time I'm taking classes from home. The other half of the time I'm in office. So if you need to see me or you consult with me, it's probably easier to directly communicate either through email or WhatsApp. Okay, so this is my number here. I've always given my number to all my students. So any questions, anything you want to clarify, you can always WhatsApp me, all right, or text me, and I'll definitely answer. Definitely, it's just about sometimes it's a bit faster, sometimes a bit slower. Okay, but I'll definitely answer whatever queries you have. Okay, so of course now that most of us are quite comfortable with online meetings, if you need to consult, okay, you can either arrange a Zoom call or through email or chat, we can settle it. All right. So besides teaching, I'm also doing quite an amount of research in embedded systems design, in robotics, and so on. Okay, so these are my research interests. I have quite a few FIP students over the past few years working on a few interesting projects, and hopefully I do get a few more to carry on some of this work. All right, so that is about me. Yeah, so these are your TAs for this semester. Okay, so some of you may know them. They may have been your peers in your EPP1 and EPP2. All right, so in fact, for this module 2271, I received an overwhelming number of signups, all right, to become TAs, but I can only choose a certain number based on the class size. So these are the 5 who are on board. Okay, so you'll probably be seeing them in your tutorials and your labs. Okay, so some of them are taking both tutorials and labs, some are just taking only tutorial or only lab. Okay, but you will see them in the next few weeks. Okay, in terms of course structure, basically we have weekly lectures every Wednesday. It used to be usually this what do you call second semester used to be on Monday mornings. Okay, the lecture used to be scheduled, but somehow there was some clash this time around, and they asked to shift to Wednesday morning, which is also fine. I think the good part is your tutorials start from Wednesday afternoon onwards, right, which is good for us so that we can make sure that your lectures are always ahead of your tutorials. All right. In terms of labs, we have 8 labs plus 1 project. I used to call it mini project. So sometimes in some of the documents, you may see the term mini project, but now I just change it to project because it's no longer mini anymore. Okay, it's quite a big project. Okay, and this is one of the key things that has changed, of course, together with the whole structure and the board and the processor you're dealing with. Okay, in terms of assessment, of course, this is important. You have final exam 40%, midterm 15%, tutorial attendance and participation 5%, and your project is 40%. Okay, so these are the components that you need to sort of get your marks in. You can see that there is no particular lab component because that lab component is sort of absorbed into the project. Okay, so I'll brief you all on that in a while. Okay, so the lab component that you will have, those marks are absorbed together with the project marks. Okay, so this is basically how you will be assessed for this module. Important thing is, do you know when is your final exam? Have you all checked? Yes, no? Okay, so let me bring up the Luminous timetable. Okay, so if you go to your Luminous module details, you should be able to see the exam date. Okay, so I hope you can see my screen that I'm sharing. So as of now, the information that we have on Luminous is that it's on 6th May. Okay, 9 to 11. All right. I'm sure all the modules already have this information, so you can probably check on Luminous itself. Okay, your exam timetable for all the different modules. Okay, so it's good to take note of all these dates. Okay, and know that you have exams on these dates. Okay, so let me come back to the slides here. Okay, next is the detailed schedule. Again, this is the schedule that is more or less I've been following through for the last two batch of students, and generally it sort of falls in place quite nicely. Okay. Yeah. Yeah. So I think, yeah, let me go through again and see whether I missed out anything before I upload any new changes to this. All right. I think one of the things that probably I need to update is this uh, week 5 where there's a Chinese New Year holiday. So there's a lab 4 there. I need to see where I can push that to, all right, and how it affects the schedule. Okay, other than that, the rest of the lecture and tutorial slots will remain the same. As far as the lab is concerned, okay, I will tell you in a while how we're going to do it. All right, and it's a bit more, there's more free play for you all, okay, so that you don't feel too stressed about weekly deliverables. Okay, but that also means that you need to make sure you keep up with the work on your own. Okay. So again, this is just the schedule. We will generally follow this. Uh, Sometimes there'll be always a plus minus or 1 week or so, depending on how we progress with some of the classes. Okay, in terms of curriculum, if you up to 19 AY 1920 SEM 1, okay, it was very different module. Then from AY 1920 SEM 2 onwards, it became a very different module. Okay, so basically what the situation was is before this time, or about 4.5 years back when I first took this module, we were running the module with Arduino, okay, Uno, okay, and I'm sure all of you are very, very bored with Arduino Uno, okay, seeing it again and again and again, okay, and it was, and the RTOS was free RTOS, okay, and there was only one sort of project board with some switches and LEDs and so on for you to learn some of the hardware concepts. And the project was also a pure software-based project. Okay, so that was how it was when I first took over the module about 4.5 years back. Okay, so I ran it one time. I really didn't feel it was doing justice to what students should be learning. Okay, and so the very first change I did was in 1819 SEM 2, I believe, or yeah, where I introduced the project component, which is to bring back the hardware element to it. But that one was still based on Arduino Uno and FreeRTOS. Then again, I still wasn't too happy with sticking with the Arduino Uno, so I decided to scrap this whole thing and switch to something else that is more relevant, more current, and something that will benefit you, correct, in terms of your learning and your experience, correct. So that is why we move to the current ARM-based microcontroller board. So it's a brand new board, brand new OS. Okay, everything is new. Okay, and I think it is for the better. Okay, because you will learn something that is much more beneficial, and I think when you put that on your resume, you put it on your LinkedIn profile, it adds a lot more value than just keep on repeating Arduino Uno again and again. Okay, so you will be learning a lot of really cool stuff. Okay, that you can be very proud of, you can brag about, and it will really be a very fun module. I guarantee you that. But of course, there is also a significant amount of work involved. Okay, in the lab. Okay, in order to make sure the project gets going. Okay, but I'll share with you some videos, okay, in some of the classes, so that you see the sort of experience that your peers have had, okay, in the past. Okay, so it is still evolving. I still have changes that I've planned for in future, uh, and some of the changes I'm going to introduce for this current batch in terms of the way we run the final competition run. But in terms of the hardware, we are still sticking with the current framework. But probably next batch, we are going to even have a slightly more advanced hardware in terms of two different computing platforms talking to each other. All right, but that I think is probably for the next semester. Okay, but for now, what you're doing is similar to what the previous batch and two batches ago did. Okay. In terms of reference tag, some of you asked me for whether you need to have any reference tag. Okay, so what I would generally say is you don't need to have any particular reference tags beyond what is already available online, as well as the notes that I'm passing on to you. Okay, there are a lot of samples and reference material online. Okay, if you just search for it. So I don't think you need to get any other textbook for this module. Okay. In terms of tutorials, we'll be starting in week 3. Okay, attendance will be marked, and all tutorials and all lectures. Lectures, there's no attendance. For tutorials, there's attendance, and it will be online. Okay, due to the class size constraints that we have. Okay, you are required to sort of participate or volunteer for at least 4 of the tutorial sessions. Okay, so this is to make sure that you do some sort of active discussion in the tutorials, okay, and engage with the tutor. Okay, it can be just some simple discussions of concepts that you want to clarify, or the questions in the tutorial itself. All right, and I think as long as you participate and you have some discussions, meaningful discussions, you will get your marks. Okay, you don't need to answer the question correctly or ask a very complex question. No need. Okay, as long as you are participating in the tutorials, all right, and I think that is what I want to encourage. Okay, you will get your full marks for the tutorials. Okay, also all the questions will be available in Luminous. I will also release video explanations of the tutorials roughly around 1 week or so after the current tutorial. Okay, so that is again to reinforce maybe some concepts that you need to just relook again. Okay, after the class has ended. Okay, in terms of lab, okay, this is the board that you're going to be dealing with. Okay, it's basically based on the ARM Cortex M0 Plus processor core, it's a 32-bit processor. Like I said, I really looked out to get something that is state of the art, is something very relevant and very beneficial to your learning. Okay, so that is why I went in this direction. Okay, so this is definitely a very, very powerful development board compared to some of the other boards that you've been using. Okay, and you can do a lot of very, very cool stuff with this. Okay, so in order to do the lab exercises as well as the project work, you need to form teams of at least 2 or 3. All right, preferably 3. Okay, because I think 3 team members would be just nice to divide up the work and to share it equally. All right, so you are free to choose whoever you want to work with. All right, so I will talk about that in the next slide in a while. Certain labs will have demo requirements. That means You have weekly lab exercises, and some of these labs you will be required to demonstrate that you have done it to your TAs. Okay, so not all the labs, but some of them. Okay, again, these are put in place to make sure that you are learning along the way and you have fulfilled some checkpoints. Okay, so during the demonstration, the TA will ask you some basic questions, okay, so that you are able, and I think the main thing is you want to make sure you understand what you're doing. All right, it's not I just uh, get some code, download, I see the LED blinking, the switch is working or whatever, and then you just demonstrate that. No, you must be able to explain what is happening, why you wrote this code this way, why do you write to this register, and so on. Okay, so if you are able to answer the questions, then you have confidence that you understand what you have done. All right, then you will be given the marks. All right. So this board that you're given is the Freedom KL25Z board. Okay, later at the end of the lesson, I will do a short demo on this board. Okay, just to give you an idea of what you expect to see in your lab 1 and after you collect your board. Okay, project. So all the items that you need for your project will be issued next week. Okay, so next week, week 2, we will be issuing you all the components. Like I said, each you're required to form the project team, and 1 robotic kit will be issued to each team. Okay, you are required to complete the assembly, okay, of the items, okay, at your own time, and then we will in the second half of the semester, when we go on to the RTOS part of it, you will develop the entire software architecture based on this RTOS, RTX RTOS, and your robot will run on this RTOS. Okay, so all the details we will release along the way. And in terms of deliverable, there is a sort of requirements checklist, and you need to be able to fulfill all these requirements. Okay, so for example, your robot must be able to blink the LEDs in a particular pattern. You must be able to play some music. You must be able to control the motors and so on. So we have a basic checklist to make sure that all the core functionalities have been implemented. All right, then on top of that, there is also this leaderboard ranking. Okay, so at the final day, the last Friday of the semester, we will have the competition run, and then based on the competition run, we will have the leaderboard ranking. Okay, so let me show you just one video. If you already seen the video, it's fine. Let me just show you over here one more time. Okay, so that was basically the video from one of the teams. All right, so I hope you enjoyed that. So that is one of the requirements for the project. Okay, where you are supposed to submit a 3-minute video at the end of the semester based on your experience with the project. All right, so there are also some requirements on what your video should contain and so on. All right, so the link for all the last semester's videos, I will send it to you. All right, at the end of this lesson, so that if tonight you can't sleep, you can just go through each and every one of them until you fall asleep. Okay, but some of them are really nice. Okay, you can see the amount of effort that they have put in terms of in the lab and also in the production of the video. Okay, so it's quite a great effort by everybody. Okay, so what is this course about? I think from seeing that video, you already have an idea that you are going to be learning basically what I would say is applied real-time operating systems concepts. All right, that means you are first going to learn the first half or the first few weeks is about advanced microcontroller programming, all right, which is the embedded systems part. And then we go on to understanding what is real-time, okay, what kind of architectures constitute real-time processing. And then we'll go into more details of how do you design and develop a multi-threaded application. Okay, so when I have multiple threads running concurrently, how do I schedule them? How do these tasks talk to each other? How do they communicate? How do you protect data and so on? So you're going to learn a lot of stuff here. So, okay, so I would say this is kind of a mixed course where we have advanced embedded systems integrated with RTOS concepts. Okay, and this was actually how it was run maybe about 6-7 years ago. All right, where the course did have advanced embedded systems with RTOS concepts, but at that time it was Arduino Uno based. All right, basically, and the reason why it changed in between was because of EPP. All right, when EPP came along, there was this thinking that okay, some of these concepts we shift over to EPP, and so we don't have to cover them again. Okay, but since I also teach EPP, I know to what extent is being covered, and I would say there's still a huge gap to be filled. So that is why I felt it's important to bring back some of those concepts back into this module. Okay, like how it used to run about 6-7 years back, and then bring in a whole new controller, processor architecture, and so on. Okay, so it has evolved, okay, tremendously over the years, and I think right now it's moving in the right direction, and it will continue to evolve further. And I think this course also prepares you well for future courses, not only on real-time systems but also on embedded systems as well. Okay, so it is a good course to take, and like I said before, it was something that you will definitely benefit from. Okay, so all the information will definitely be available in Luminous itself. So everything I'll upload there. At the same time, all the videos for the Zoom sessions as well as tutorials or anything that I want to explain, I will create videos and upload to my YouTube channel. Okay, so my website and YouTube channel are here, so you can always reference them. Whenever I upload anything that is relevant to all of you, I'll send you all the link as well. Okay, so that you know that there is a video release giving you some explanation on something that we have discussed or that you need to know. Okay, so some motivation I would say is important. And one of the things is basically, I think 2020, though there were a lot of challenges because of COVID and so on, it was also interesting in a sense that the whole processor war sort of reignited. Okay, and it was interestingly taking shape because suddenly you have AMD coming up with very powerful processors, okay, Intel trying to catch up, and then you have Apple coming in and releasing their own silicon, all right, and then there's talk on Nvidia and ARM also coming together. So there was a lot of interesting and exciting news about things happening in the processor and the microcontroller world. Okay, and I think it's good for us, correct? Because when there's innovation and there's progress by these kind of companies, it translates to better processors, microcontrollers, development tools for us, correct? So I think it was an exciting year in that sense, where we saw a lot of this news coming out. All right, so hopefully that improves, all right, and things get better for us in terms of the kind of tools that we are able to deal with in the future. Okay, another thing also is, I think in Singapore, you would have probably heard the buzzword of the smart nation, all right, being floated for quite a few years already. And there's actually a lot of work in terms of research and project going on right, on how to make things smart. All right. I think one of the most misunderstood concept is when you say smart doesn't mean that it has to be, you put some sensor, it just automatically gets some reading and then, okay, that you call it a smart system. Okay, so that is one part of it. All right. Uh, I think when you say smart means you want to make sure that at the end of the day, the day-to-day activities of things that we do improve because of this innovation and this technology. Correct. So how we want to innovate, okay, how we want to put things together. Okay, I think that is the fundamental skill set that all of you have. But as computer engineers, you are in a very, very wonderful position because you have skill sets and knowledge in both software and hardware, and you know how to put things together. All right, I think that is your biggest advantage. All right, so you can always use that advantage, okay, to innovate, to create. Many of our CEG students in the past have come up with their own startups, okay, their own ideas. Some carried on, some left it halfway, and so on. Okay, but I think there's definitely a lot of support, all right, for our students in terms of startups and giving you space or even funding. Okay, so if you are interested, okay, you can go and find out further. Okay, we have NUS Enterprise within SOC also we have our own grants. All right, so many students have benefited. All right, maybe some of you already are working on your startup with some grants and so on. Okay, so I think CEG students have a unique advantage, okay, for this. So do always keep an open mind, and whatever you learn, think of uh, whether you have some idea that you think you want to implement with whatever knowledge you are getting through all these courses. Okay, so let me just do a quick poll before we end this first lecture over here. All right. Okay, so this poll is for me to just get a feel, okay, for your own sort of confidence level. Okay, so answer honestly because I do not know your name or no information is collected. All right, so just answer honestly, and I just want to get a feel for what you yourself think about your current level of expertise. Okay, so I'll be ending the poll now. Let me share the results. Okay, so basically two questions, correct? One is your confidence level with hardware prototyping, and the other is your C programming. Okay, so for hardware prototyping, I think about more than half of you say you're okay about it, all right, which is good. Okay, so in terms of hardware prototyping, I think from the video you see there is a fair amount of wiring or soldering and putting stuff together, okay, that you need to be comfortable with. Okay, that is definitely something you have to do. So since you're working in teams, okay, at least make sure that one person in the team is confident or is able to take on this kind of tasks. Correct, so that you have somebody who can handle at least the hardware aspect of the system. C programming is definitely a must, correct, because we're going to deal with it extensively throughout the whole module. Okay, so most of you said your level is intermediate, which I think is good. All right, so as long as your basic C programming concepts are there, okay, then you shouldn't have any issue. All right, so basically we will apply C programming in the first half for all the low-level device drivers that we will be working on, and in the second half will be C programming for the multi-threaded application. All right, so that is basically what you need to be working on. Okay, so I think it's good. The results are good, and I think you should be in a good shape to take this module. Okay, now what I'm going to do now is this. Okay, I'm going to give you a short break, but before I give you a short break, I'm just going to show you the Luminous page. Okay, so in the Luminous page over here, under class and groups, okay, there is a class groups and a project groups here. Okay, now the team enrollments are all over here. Okay, so later, okay, once you have formed your team, you can enroll yourself into any of the team numbers here. Okay, it does not matter which team number you choose. Okay, you can choose any team number, but you need to make sure you form your team first before you enroll in this Luminous group. Okay, and once you enroll in the Luminous group with your team, you cannot change your team after that. Okay, so make sure you know who you are going to form with. All right, discuss with your friends, form your groups, and then you enroll. Like I said, the team number doesn't matter. Okay, the assessment is not going to go in sequence like this. It is just for admin purposes only. All right, so the team number here does not matter. Okay, so what I'm going to do is I'm going to give you a short just 5 to 10 minutes break. Okay, just to relax a bit. I'm going to come back and I'm going to go on to the lecture, next set of lecture slides, where I'm going to talk a bit about embedded systems and the architecture design and some important matters again for the next week's lab and what you need to do. Okay, so we'll just have a short 10-minute, 8 minutes break. Now it's 10:42. I'll meet you back here at 10:50. Okay, 10:50. Okay. Okay, so again, do not rush to register your groups yet until you make sure you already have your team with you. Okay, then you can go ahead to register. Okay, so there will not be only any auto assignment of team. Okay, once you form your own team members, you come together already, 2 or 3 of you, you can go and register in any of the team numbers here. For those who do not have or not able to find a group, okay, I will talk about it later, okay, on what we will do. Okay, so don't worry, go for your break first and come back. Okay, later I will talk about more details about this. Okay, so welcome back. All right, so towards the end of this set of lecture slides, I will talk a bit more on the project and what you need to do to get prepared and to collect your components next week. All right. Okay, so this set of slides is basically to just give us some background, all right, in terms of introducing you all to, again, not say introducing, more revisiting the concept of the embedded systems design and give us some idea towards where or what we're trying to do here. Okay, so exactly what do you say is an embedded system? You can say it is a computing platform or computing system. Only thing, it is very application specific. Correct, just like your camera, your phone, your GPS, your MP3 player, they are all computing systems. Correct, only thing is they have a specific application in mind. All right, and in general we say that such embedded systems are designed to be interconnected or integrated into larger systems. All right, just like your mouse and your keyboard and your camera and so on, these are all specific embedded systems, but they are meant to be integrated to a larger workstation, right? Now, effectively, why do you want to add computing resources? It is quite obvious, correct? You want to have the performance, the features, and the ability of a computer inside our system. So, better performance, features, functions, and so on. All right. And one of the things is, of course, microcontrollers or embedded hardware or computers. Generally, when you produce a device or a system, it's for the mass market, which means your non-recurring engineering cost. Okay, so when you design a product, okay, you might probably study this in some other module for product design. Okay, so there are two costs involved. Okay, one or two factors involved. One you call it NRE, and the other is called TTM. Okay, so this is more of a business and marketing perspective of things. So the NRE is basically what you call the non-recurring engineering costs. All right, so these are the costs involved at the upfront, all right, where you want to design and develop a product, but subsequently you do not need to factor them in because your overall cost will be reduced when you mass produce it. TTM is basically your time to market, all right? And TTM, why when you have a startup, you want to launch a product, your TTM is important because you want to make sure your product can be released in time to capture the market, right? While the ground is still hot and people are still wanting to have such a product. Right? Once that interest dies down, then nobody wants that product anymore. Okay, so in terms of embedded systems, your upfront cost is high because you need to work with a lot of engineers and tools and development boards and so on. But subsequently, when you mass produce it, your cost will go down tremendously. All right, because you only need to focus on the important part, just like your Arduino Uno board, okay, or even this freedom board you're going to deal with. If you look at the Arduino Uno board, okay, I think in EPP2, at least those who were in my group, we went through in quite detail about the schematic and how it is interconnected and so on. All right, but ultimately it comes down to just a few components, correct? It's just your main AT3280 microcontroller. You have your power, all right, you have your clock, and then you just need to connect up your uh, the required GPIO pins or UART or PWM to whatever is your application. Right. So if technically you can shrink down that entire thing to a very, very small scale with very, very little components. And when you just focus on the IC chip alone and these subsystems, your cost will come down tremendously to just a few cents. Okay, so again, it comes down to practically a few cents or just maybe a few dollars because you're talking about mass production, correct? In tens of or hundreds of thousands of units. Okay, so that is basically how you can actually scale down your design eventually when you want to mass produce. Okay, of course, some systems may also be networked where you are going to talk to each other, all right, over the network or over some data protocol like what you did in your EPP2. Okay, so of course, what are the options we have for building such embedded systems? All right, so what we know, all right, so far is this: using microcontrollers, all right, which have integrated memory and peripheral subsystems. Okay, if you want to use your own processor core and then you want to build your own system, then you can also do that. All right, but then it is of course a lot more effort involved in terms of designing the system and building it up from scratch. Okay, because you need to take a processor core and then decide how much memory you want, what kind of peripherals you want to interconnect, and then build your own sort of microcontroller. All right. Embedded PC is basically something like a microcontroller also, but it is again a more high-end device for industrial applications. On the other side, you also have FPGAs. Okay, some of you may be doing or may have done some modules on FPGA. In FPGA, basically, you are going to write code called HDL, Hardware Description Language. Okay, and the two languages you'll use either Verilog or VHDL. That is also another popular way of prototyping systems. And that is very useful. Okay, FPGAs are very useful when you want to design your own hardware. Okay, you want to design your own processor, you want to design your own network, integrating chip and so on. Okay, but the problem with that is when you want to scale it, okay, you need to think whether it's cost effective. All right, so usually the next stage of FPGA is when you want to scale it to mass production, you go towards the ASIC. So in ASIC is already a customized IC chip. So like your ARM processor, your 8 mega processor. So the processor core itself is basically an ASIC chip, right? But it was designed as the first stage of FPGA, and then they finalize it into an ASIC chip for mass production. Correct. FPGA you can still rewire it on the ground, correct, technically, but in ASIC is already hardwired, so you can't change it. Correct. So in terms of flexibility, upgradability, while the product has already been shipped, you only have two options. Either you go with the FPGA option or the microcontroller or microprocessor option. Okay. Discrete logic is of course you putting together your AND gates, OR gates, NOT gates, and then building up a system. All right. So that is definitely may still be effective for very simple systems. Okay. Once the complexity goes up a bit, it becomes a bit cumbersome to even think about it. All right. Because when your system's complexity goes up, then you need to come up with a whole new truth table, draw a whole new K-map, try to simplify and come up with the logic and so on. So it's not practical, correct? So the microcontroller based option, it is still a good and easy option to start with, correct? So that is why boards like this, Freedom board, the Arduino board, and so on, they are very popular for startup companies because you can easily prototype and get a proof of concept very quickly, and then subsequently you can think of the next phase. Okay, when you want to mass produce, you want to shrink down the cost and the size. Okay, then you look at the next stage. But to prove something, a proof of concept, to demonstrate that this idea is feasible, microcontroller boards are definitely the best option moving forward. Okay, so let's look at a simple system here. So this is like this is basically what you call a bike performance tracker. So those of you who ride bikes, I mean here you're talking about bicycles, all right, racing bicycles or mountain bikes and so on. So you can fix this kind of devices, okay, with appropriate sensors to your wheels and so on to monitor how you're performing, all right. And the main idea is you want to measure your speed as well as the distance. So what are the constraints? Okay, so if let's say you join a company, you're supposed to design something like this. Okay, what would be your constraints that you look at? So you want to make sure that the size is there, is compact. It must be cheap. Okay, it must run on a very simple, probably a small cell battery, and it must also be very lightweight. Okay, in terms of inputs, you have some sensor. Okay, so you have some sensor connected to the wheels or the frame or something to tell you how the wheels are rotating, how far they're rotating, similar to your sensor you use in your EPP2. And then you may have some button, okay, somewhere over here, or just to press and to change the mode, change some settings and so on. Okay, as the output, you have a display. In this case, it's a very low cost LCD display. And in terms of a controller, you just have a simple 8-bit controller is more than enough for this. Okay, how about if you go up to another extreme, a gasoline automobile engine control unit? Okay, so all automobile vehicles, all right, have what you call an ECU, engine control unit, which is a very complicated piece of equipment because it has a wide range of functionality that it needs to be able to carry out, correct? So in terms of monitoring, it needs to take in inputs from a lot of different type of sensors. Okay, your accelerometer, your battery, your oxygen, your fuel pressure, as well as your clutch, your brake, and so on. Okay, at the same time, taking all this information, it needs to process this information and then decide how to control the device, correct? In terms of output, you have relays, your cams, your valves, and so on. Okay, in terms of your speed and your stopping of the car, okay, you have your injectors, your spark plug, your throttle. So this engine control unit is definitely a very complex device, all right, which has a lot of tasks that it needs to fulfill in real time. Correct. So you can see that engine control unit, the performance has to be in real time. Correct. When you are driving a car, you press the brake. Okay, you expect that the car will stop within, or the brake system will kick in, or the ABS will kick in within maybe 100 milliseconds or something. Okay, so there will be some requirement you need to fulfill, and it has to be done. Correct, because it is a life or death situation. Right, it's a very important piece of component that controls or plays a part in the life of a person. Whereas you compare to a bike speed monitoring system, if it occasionally fails once a while, it doesn't update so frequently, it is still fine. All right, it does not have any critical impact on the user. Okay, so the application should be a basis to decide what kind of a system you want to use. So for something like this, you definitely need a high performance MCU. Okay, something like this 32 megabit, lots of memory or enough memory for the system to run, probably even a OS. Now, since this is about gasoline automobile systems, it's interesting to know that there is actually standards for different type of systems. So have any of you heard of this term called MISRA before? Yes, no? Okay, so MISRA is basically, okay, maybe I will, I mean, you can Google it later. It's basically a standard, okay, for writing software for the automobile industry. All right. So if you join a company like, let's say, General Motors or Delphi or so on, Continental Automotive. Okay, so these are some of the companies that are actually having R&D centers here in Singapore itself. Okay, so if you join any of them, okay, maybe as an intern or even later when you graduate, okay, when you write code, okay, there are specific standards you have to follow because you are writing code that is going to be running on a car, okay, or an automobile vehicle. Okay, so it is very important that you follow the rules laid out by this framework, okay, to make sure that uh, if anything goes wrong, there is a proper way of dealing with it. So this MISRA actually has a lot of standards in place on how code should be written, what is allowed, what is not allowed, or how do you handle failure, how do you handle functions and so on. So they have detailed rules about how code should be written. Okay, and this is very important for this automobile industry. Okay, so again, benefits of embedded system, I think we sort of know it uh, quite well. Right? We have seen it before. The efficiency, the cost, the features, and so on. Right? So I will not repeat all of this again. Okay. Again, with embedded systems, you are able to have closed loop systems. You can do a lot of signal processing. Okay. So another branch of embedded systems or microcontrollers is what we call DSPs. Okay, DSP stands for digital signal processor, and DSPs are also embedded microcontrollers, but they are designed specifically or for applications where you needed to do a lot of signal processing. Okay, so if you look back at your mathematics, okay, of signal processing, if you look at Fourier transform or wavelet transform or anything like that, you can see that it involves a lot of multiplication, a lot of uh, addition, and so on. Okay, so there's a lot of mathematical steps involved when you talk about doing uh, signal processing in general. All right, and so a processor the processor architecture in detail you will study in other modules, but basically I think all of you know that we have this thing called the fetch, decode, execute. Correct. So we fetch an instruction, we decode the instruction, and then we execute the instruction. Okay. And in most cases, okay, in most microcontrollers, multiply instructions or divide instructions tend to take many clock cycles. All right, so that can delay the throughput time, okay, of trying to do signal processing operation on a normal microcontroller. So that is why they came up with this concept of DSP, where the controller itself has a lot of what you call MAC blocks, okay, multiply and accumulate, okay, MAC, multiply and accumulate blocks. And why multiply and accumulate blocks are important? Because these hardware blocks are the ones that are very often used in signal processing applications. Okay, so by having dedicated MAC blocks inside your processor, you can speed up signal processing tremendously. So that is another branch of embedded system controllers. Okay, so many years ago, DSP chips used to be very popular, but again, with improvement in technology, nowadays more and more controllers are coming with integrated DSP functions. All right, that means you have a controller that you have can execute all the instruction, and you also may have a separate DSP block integrated into it, so you can also perform signal processing applications very efficiently. Okay, so you don't need to have a separate DSP chip for that. You can do it together in one particular chip itself. Okay, so attributes of embedded systems. Okay, you want to interface to analog signals or digital signals, or whether it's input or output and so on. Okay, so take for example this. All right, you have a analog pressure sensor here, and this is a analog sensor. Correct. So if I want to integrate this to my microcontroller, all of us have used the A to D converter in the Arduino Uno before. Okay, and you can also use something similar over here. All right, in the Freedom board. Okay, so basically you try to look at what is the relationship, okay, between the input and output in terms of, in this case, pressure and output voltage. So when you measure the output voltage, you can recalculate what is the actual pressure of the system. Okay, so that is basically the idea of A to D conversion. Now, interestingly, of course, this is easy because this is just a straight line, it's linear. But what if the relationship between the output and the pressure is non-linear or disjoint? Okay, so for example, if I were to say that the relationship between the output voltage V and the pressure, okay, instead of it being a straight line, okay, I say that it is maybe it is disjoint. That means it goes like this and then comes like that. Okay, so if I say that this is how the waveform looks like, then what do? Because it's not so straightforward anymore. This one is just a straight line, so I can just use my straight line equation to represent the relationship. Okay, but now it is not so easy anymore. So if this is the sensor and this is the relationship, then what do? Any suggestions? Okay, so you can just put in the chat what your thoughts are. What do you think you can do? Anyone? Hard code, discrete data points, lookup table. Okay, good. So all these are split the graph to useful sections. Okay, good. Okay, so all of you have given all different possible solutions. Okay, so one, you can say you hard code. All right, so if you hard code is possible, that means you take into account all the different pressure values and you hard code the appropriate voltage values in a lookup table, and then you can reference that table to get the reading. Okay, the other alternative is you can break up the graph, okay, into sections. So you can say that, okay, this part I can approximate using a linear, this part I can approximate using a linear, and so on. So you can make a non-linear graph piecewise linear. Okay, this is what you call piecewise linear. That means different pieces of them, you can approximate them to be linear functions, and that can speed up or simplify the analysis. All right, so you look at different sections of linear relationships. Okay, so again, all these are important things to understand and to know, because in reality, when you are given a sensor, you may not have the option of choosing something else. So you may have to work with what you have, and then you need to think of what is the best way to deal with it. All right, and of course, you can also look at it from a practical perspective to say, okay, I'm going to use this sensor. Okay, and though this sensor can sense a pressure over a wide range, okay, from 0 to 260, okay, but maybe you're only interested, okay, in values from 80 to 120, correct? So maybe all you are interested in is maybe this 80 to 120 here. So you can ignore the rest and just say, I just look at these two sections and try to approximate or make it linear and so on. So you can look at it from a practical perspective also to say, instead of trying to write software to cater to all the possible input values, I just want to focus on the input values that I know my system is going to give me, correct? Because this is the way it is wired up in the hardware. Okay, so there are a lot of different ways in which you can approach the problem, all right, either in the software perspective or the hardware perspective. Okay, so microcontroller versus microprocessor, this is something you should know. Basically, a microprocessor is the core, all right? So in our case, in the Freedom board, okay, the core is the ARM Cortex M0 Plus, all right? So that is the processor core that will eventually fetch and decode and execute all our instructions for us, all right? Now, in order for this processor core to be able to work, or any processor core to be work, you need some peripheral subsystems to be integrated. Okay, the main things are definitely your memory, correct, your power, and your clock. All right, so these are the main things that you need in order to make your system work. All right, and when you have a microcontroller, basically what you are getting is the manufacturer has already integrated your core with all these subsystems and given you as a single chip solution. Okay, so the Atmega 328P that you are using, this KL25Z board controller that you're going to get, all of them are single chip solutions. That means everything is already integrated into one IC chip. Okay, so you do not need to worry about connecting memory, connecting a clock system, connecting timers, and so on. So everything is integrated to one single chip, and that is what we call the microcontroller. Okay, in terms of real attributes of embedded systems, okay, what we want is we want the systems to be concurrent, okay, and reactive. Okay, so when we say concurrent means you must be able to do things in parallel at the same time and must be able to react, correct? So if I press a button and I expect the LED to be on or the sound to be activated, I want that behavior. It must be able to be reactive. Okay, so in terms of concurrency, okay, there is the hardware part and the software part. Okay, so the hardware part is where these peripheral subsystems come in. All right, so for example, I want to make sure that every 1 second I send out a data packet. Okay, so for example, I have a controller and this is my UART, my serial port, and I say every 1 second I want a particular bit pattern to be sent out through the UART. Okay, so how can I do this? Okay, because my controller will be busy using other things, all right? So I can use my hardware systems to do it. At the same time, we also know that we have learned the concept of interrupts before. So interrupts also help us to achieve a level of immediate reaction, so that regardless of what I'm doing, I can momentarily pause it and go and do something else. Correct. So what I can do is I can say that I can configure the UART to send out this data packet every 1 second, and this 1 second can be triggered by maybe one of my timer blocks over here. Okay, so every time the timer overflows or triggers an interrupt, I launch my UART interrupt to send out this data packet. All right, and all this can run concurrently in the background while my microcontroller is doing other things. Correct. So we already have a sense of real time and concurrency for what we already know. So even before 2271, we were having some level of real time and some level of concurrency. All right, so that is basically making use of what we already have in our microcontroller, okay, in terms of interrupts, in terms of the peripheral subsystems and so on. Okay, so in this example, okay, I want to initiate interrupts, okay, to do my A to D conversion, okay, at periodic intervals. Okay, so what I can do is I can configure my timer block to give me periodic interrupts. So once I start the timer, okay, at a particular interval, the timer interrupt will trigger and I'll jump to my timer ISR. In my timer ISR, I start the A to D operation. And in this case, I allow 4 interrupts to be generated, okay, for my A to D peripheral block. And each time my A to D interrupt is triggered, I'm jumping to my ADC ISR. Okay, and every time I complete this, I say my ADC operation is done, and then I start the next timer interrupt again. Okay, so you can see that in this situation, whatever that is happening over here, this time period, I'm actually freeing up the processor to do anything else that it wants, because the whole timing, periodic timing interval and A to D operations are all handled by interrupts. Okay, so I just need to start it, and then subsequently I can do what I want until everything is done. Then I get a notification, and then I'm able to start the next one. All right, so this is basically what we are able to do using even simple controllers like the Arduino Uno. All right, to configure a sequence of tasks to run periodically in nature. Okay, so of course some of the things that we also need to do is of course fault handling and diagnostics. All right, that means if something goes wrong, how do you handle this? Okay, in most cases, we don't do this frequently in projects that we do in school, but in reality, you need to be able to handle it. Correct? If you just take your EPP2, for example, okay, you are remotely controlling your robot. Correct? You're not physically there. Uh, how do you know that you still have control over all 4 wheels? Correct? Do you have a mechanism to know that something has gone wrong and you lost control of one of the wheels? Correct? So there must be a way for you to detect that something is wrong, and after you detect something is wrong, what should you do? All right, so fault handling code is important because you need to be able to put your system to a fail-safe mode to make sure that it does not cause more harm than it should. All right, you do not want your search and rescue robot, because one wheel got punctured, go and bang the survivor and kill the lone survivor down there. Correct? Okay, so if your system has failed, okay, you have lost control or something is wrong, you must be able to put it into a proper mode so that you can sort of service it or get to it to repair it before you start using it again. Okay, so again, these are the constraints that I think we have seen before again and again: your power, your size, and so on. Okay, in terms of constraints, okay, in terms of size, generally what we want to look at is the memory that we have. Okay, so in microcontrollers, definitely you want to look at on-chip ROM and RAM quite importantly, okay, before you start a project. Okay, that's why whenever I deal with students who are going to do the FYP or any other research project, okay, when they say they want to use this microcontroller, I ask them to go and check again and again whether you are sure that this controller is the right choice for the project that you're going to do. All right, because you start off with one microcontroller, you design the hardware, you design the interfacing, and just a few weeks before the end, you realize that you have run out of memory, correct? Because you wanted to implement some new feature, and this controller, the built-in memory is too small, and you don't have enough memory, you are stuck. Okay, so you always need to do some analysis on how much resources you need and whether the controllers you are using or you're going to select are the right ones for your project. In terms of programming language, embedded wise, C is still the #1 choice. Okay, and in terms of operating system, uh, generally you may need, you may not need. Okay, so one of the things that I think is important for you to learn towards the end of the module is when you finish this module and you learn all about OS, you will tend to feel that, yeah, yeah, OS is really fantastic. You can do a lot of great things with it, and you want to integrate OS into all your projects in the future. And the first thing I will say is don't do that. Okay, because the OS or the RTOS that you're going to be learning, or any other RTOS you're going to deal with, is a very powerful tool. Okay, but you may not need to use that tool all the time. All right, it all depends on what is the project that you're working on, what are the constraints, what are the requirements, and then you choose the right tool for that. Okay, so do not choose the RTOS and put it in just because you know RTOS. Okay, in some cases, without the RTOS, just a normal super loop with interrupts and so on may be enough to solve the problem. Okay, so do not use the RTOS if it is not necessary. Okay, only when you think that there is a proper justification for integrating the RTOS in the project, then you go in that direction. Okay, so this is the basically the board that you're going to be issued with, the Freedom KL25Z board. Okay, so it's a very powerful board, like I said, running a very high clock rate, 48 megahertz, with more than enough RAM and ROM for all your software. Okay, it's roughly around $24 if you buy it locally. Okay, SG, so element 14 and so on. Okay, uh, so in terms of writing software, okay, okay, so again, when I was looking out for a board to do it, all right, when I came abroad, bought this board, okay, the first thing that I saw was it is compatible with this platform called the Embed OS. So the Embed OS is also another popular OS which is developed by ARM itself, and there are many boards that are supported by this Embed platform. Okay, so let me show you that. Okay. Okay, so this is basically the ARM embed. So maybe if you click on the boards here, you can see that under development boards, okay, there are a wide range of embedded boards supported by this platform. Okay, okay, so there are a lot of them. So I will not go through all. Okay, so let's go back to the KL25Z board. Okay, that we were looking at just now. Okay, so this Freedom KL25Z board also supports the Embed OS platform. All right, and Embed OS is basically another RTOS that is developed by ARM itself. Okay, to promote their OS and promote their boards. Okay, and but we are not using Embed OS for this particular module. Okay, for two reasons. Okay, so the first reason is if you come to this page and you look at the software. Okay, the software that is given, or the kind of software you can actually write with Embed OS. Okay, okay, you can see that it sort of uh, goes against the philosophy of why we even moved away from Arduino Uno in the first place. Okay, because with Arduino Uno, you are always using your library functions and you have some exposure to some low-level programming in EPP. Correct. Over here, you can use again very high-level abstracted library functions that will really make your life easy for programming, but in terms of learning, is very bad. Okay, so that is why I decided not to go ahead with this option. But there is a way to do low-level programming with Embed OS as well. All right, but again, why I'm not using it is because when you go to the OS portion later on, the way the Embed calls the OS related functions is a bit different from how most other operating systems in the market work. All right, and so I want you to get that exposure that is more relevant. All right, so that you know exactly how to use OS kernel calls in the way that they have been written by the producers or the manufacturers of the OS. Okay, so that is the reason why we are not using embed OS. But okay, this is just to let you know that this board is compatible with embed OS. All right, but what we will be doing is we'll be actually using the Q platform, okay, which I will show you in a while. Okay, so this is the board that you will get. Okay, all right, so let me share with you some important information for next week first before I demonstrate the board using the Q platform. Okay, so important things that you need to do. Okay, so you don't need to do it by end of today, but as soon as possible. You need to form your groups and register them in Luminous. Okay, so just now I showed you the page. You can use any team number. Okay, so you need to make sure you register them as soon as possible. Okay, important thing, this is common question everybody will ask. Regardless of your lab schedule, you can have any team. That means it doesn't matter whether you are in lab group 1 or lab group 2. Okay, it does not matter. You can form group with anybody you like. Okay, so whether you're group 1, your friends are in group 2, doesn't matter. You can form them together. Okay, preferably you just stick with one group, so all your weekly lab sessions and your project work you do with the same group of friends. Okay, you only need to register your project group in Luminous. Okay, so there's no other group that you need to worry about, and you should register it after forming your group. So don't just go and register under some team name right now. Okay, make sure you have discussed with whoever you want to partner with. Okay, and you all agree that okay, you all are going to come together and form this project team. Then you go and register in Luminous. Okay, some of you, okay, may be working remotely the entire semester. Again, this is only applicable for those with valid reasons, because I know some of you have been emailing me and contacting me that uh, you are unable to travel back. All right, so I will be sending out a Google form link later to capture this information for those who are genuinely affected. All right, so if you are one of those who are potentially going to be working remotely for maybe at least quite a while, okay, in this semester, please make sure you already tell your teammates about this and plan this accordingly. Last semester also we had the same issue. In fact, last semester we had quite a few students who were stuck overseas, and they worked remotely with their teammates. All right, so they divided the work. They had Zoom sessions. They collaborated and so on. So it's not an issue. Okay, it can be done, but just make sure that such things are already discussed with your teammates. Okay, so that everybody knows what is happening. Okay, choose your teammates wisely. Okay, so unlike EPP1, EPP2, that you have cases where there's always some unhappiness when somebody in the team is not pulling their weight. All right, then you say, okay, that fella is not doing his job, he's always doing his own things and so on. But in this case, you are given the freedom to choose your own teammates, so you should not complain after that. Correct, so choose your teammates wisely. Okay, once you register them in Luminous, you cannot change after that. Okay, so make sure you discuss, you choose people who you can work with, and you form a team. Okay, the last one is important. What if you don't have anyone to partner with? Okay, so again, this could be a case where you have friends, all right, not that you don't have friends, but it's just that they already formed teams before you were able to contact them, correct, and they already registered and there's no more space available. Okay, so I will be sending out another link later to collect information of students who are unable to form teams, and then I will group you all together. All right, so this is again if you really are unable to find anybody to partner with. Okay, generally what I will do is, okay, those teams that only have 2 teammates, all right, I might see if you can take on one more student, okay, and make it a team of 3. Okay, if not possible, then I will group the rest of them who don't have teams into separate teams. Okay, so that is how I will deal with students who are unable to form their own team. Okay, now next Friday, okay, you must come to the lab. Everybody must come to the lab. Okay, again, you do not need to come to the lab only, or if you have a valid reason, your MC, your stay home notice, your overseas, okay, those are valid reasons. Other than that, you must come to the lab and you must come according to your lab schedule. Okay, why is this important? Because next week, each project team will receive their project kit. Okay, so you will receive a goodie bag, okay, with all the required components inside. Okay, your like what you saw in the video, your motor driver chips, your regulators, your Bluetooth, your connectivity boards. Okay, everything will be there. Okay, and one team member of the team just needs to check through all of the items and then sign off that you have collected them. Okay, on behalf of the rest of the team. At the same time, okay, each student will also receive one Freedom KL25Z board. Okay, so every one of you, that means 100 of you, each of you will receive your own Freedom board. Okay, this is for you to keep throughout this entire semester. Okay, for you to do your lab experiments. Okay, as well as work on the project. Okay, please be careful, extra careful with the board. Okay, one thing we have seen again and again is it is a very sensitive board. Okay, that means you must be very careful that you do not touch it if your hands are wet or damp. Okay, store it in a proper place and so on, and do not let spare components or parts just drop on your board and things like that. Okay, it's quite sensitive, so deal with it very carefully. Okay, so that is why each student is given one. There is no replacement board. Okay, so what you need to do, okay, if something goes wrong, uh, like what I mentioned in the announcement, each team is given a budget of $40. Okay, for you to buy stuff related to the project. Okay, if you're not buying anything, okay, or you're not using the money, you can buy one additional board. Okay, for the team if any of you damages the board. But again, uh, don't start off with that thinking, because like I said, only one board is probably you can replace with the current cost. Okay, so if you can keep the board properly throughout the whole semester, I think it's good. Okay, now after you collect the board next Friday, okay, what you must do is you must do lab 1. Okay, so lab 1 I have already uploaded. Okay, you must do lab 1 and make sure that it's working as expected, as laid out in the lab sheet. All right, why is this again important? Because you need to make sure that the board is fine and everything is good before you leave the lab. Okay, if there are any issues, it's not running, the LED is not blinking and so on, you must inform the TA to have a look and see what is going on. Okay, sometimes you may have just not done one or two of the steps correctly. Okay, and then that's why it's not working. All right, so make sure you get lab 1 working. So lab 1, you don't need to do any coding, nothing. It is just to set up the board correctly. Okay, probably 15 to 20 minutes of your time, that's all. Okay, once that is done, you are free to leave the lab. Okay, but you have to do it before you leave the lab. Okay, so that is all I have for the lecture. Let me just show you a quick demo of the board and the Keel IDE. All right, so that you know what to set up and what to prepare for next week's lab. Okay. Okay, so in your Luminous, I've already uploaded the Keel exe file for you to download and install. For now, from what I know, there is no Mac version available. So the students who are currently using Mac in the past few semesters, what they have done is they have installed some virtual Windows environment and then install Keel on it. All right, so that is the current option or the only option available for now. Okay, so if you are a Mac user, you have to do this in order to run this software. Okay, so this is basically when you launch Keel, you will get a similar environment. I think most development environments have a similar layout. You have your project panel, you have your coding environment, and you have your build output here. Okay, let me show you the board over here. Okay, so this is the board. Let me zoom in. Okay, so this is the KL25Z microcontroller board, okay, that you will get. Okay, so this IC chip here, that is basically the main ARM processor core, okay, or the main microcontroller chip, okay, with the ARM processor core inside. This panel here is a sort of a capacitive touch sensor here, but we're not going to be using that. All right, the important thing is, okay, these header pins, okay, that you see here, what I will issue to you separately, and you need to solder them onto your board. You don't need to do it next week, okay. You only need to do it for lab 2 or lab 3 onwards, okay. I'll let you know. Okay, for next week lab, you just need to collect. You don't need to solder anything, you just need to test the board. Okay, when you first collect the board and you plug in the USB, okay, so there are two USB connectors here. Okay, one is what we call the KL25Z connector, the other is open SDA. Okay, so you need to connect it to the open SDA pin over here. So all these I already explained in the lab manual. Okay, so by default, okay, when you connect your board, okay, it is pre-configured to run with the embed OS. Okay, so in the embed OS, your board behaves like a flash drive when you plug into your computer. All right, so if you look at your manual over here, your lab 1 manual, okay, so this is the lab 1 manual you need to go through. So I've given you all the instructions step by step what you need to do. Okay, so when you first connect your board, okay, it will behave like a flash drive, and at the same time when you tilt the board, okay, when you tilt the board, it will actually um, sort of change the RGB. Okay, so that now I don't have it because I already upgraded my board. Okay, but by default, when you plug in, the RGB LED will light up, and as you tilt the board, because it has a built-in accelerometer sensor, as you tilt your board, the RGB LED will change colors. All right, but what you need to do is in lab 1, these instructions here, uh, again you go through step by step. Okay, when you have the board, what I'm asking you to do is to reconfigure the board, okay, so that instead of being compatible with embed OS, it is going to now work with the Kill IDE platform. Okay, so once you are able to do that successfully, you are going to use this environment, the Kill IDE, to write your software for the rest of the module. Okay, this setup that you're doing in lab 1, you only need to do it once for every new board. Okay, subsequently you don't need to do it again. Okay, so you only need to do it once, and once you have done it, you can use this Kill IDE platform to successfully run all your code for the future lab sessions onto the board. Okay, so once you have it and you connect up your board, okay, so let me do this. Okay, so I'm just going to run the code to show you what happens. Okay, so once you have connected up your board over here, and you open up the default code, which is the Blinky code, okay, you can build your code. So you go to project build. So your build output over here, you should not get any errors or any warnings. All right, basically because this is the default code given to us. Okay, under debug, there are a few things that you need to do. So uh, basically, let me show you over here. So under options, again, you don't need to write down anything now. Okay, all of these are already explained inside your lab manual. Okay, so since we are going to debug mode, okay, there is this setting here that you need to select the CMSIS DAP debugger. Okay, once all of this is done according to the lab manual, you can go to start debug session. When you click on that, you can see down here what is happening is you are basically downloading the code to the board, and you can now do debugging. Okay, so in debugging, the good part is you can actually set breakpoints, all right, which we'll be doing in subsequent labs. So you can set breakpoints, you can examine memory, you can examine registers, variables, and so on. So that will help you a lot in debugging your code, okay, if things are not going so well. All right. So for the default code that you're going to be running next week, when you click on run, you should see that the LED will keep changing between the three colors R, G, and B. Okay. So again, this is default code that is given to you. The objective of that one is just to make sure that your board is now configured correctly. Okay, and you are able to run and see that the RGB LED is blinking in sequence like this. Okay, so that is the objective of lab one. The material is already there, it's uploaded. What you need to do is you need to make sure that next week when you come to the lab on Friday, okay, you have already installed your Keel IDE environment, all right, and you have sort of downloaded the manual. And once you collect your board, you can straight away test it out. Okay, you don't need to do any soldering next week, you just need to test out the board. Subsequently, you need to do soldering. Okay, so for the soldering, I will give you the connector boards again next week when you collect it. Okay, let me just show you the soldering here. So as you can see, the soldering has to be done neatly and very nicely. Again, this is important. Okay, why I say it's important? Because if your soldering is not done correctly, there's a high chance you will damage your board and you can't use it again. Okay, that is one thing. And at the same time, I also have students who have soldered the pins the other way around. That means instead of the header pins coming out on top, they have soldered it with the header pins coming out over here. All right, so please be very careful. Okay, if your soldering is not so good or you're not so confident with it, get one of your friends who is good to help you out. Okay, for the board alone, I would say it's okay, just get some help, because if your board you don't do it properly, you solder and you create a lot of short circuit here and there, chances are your board will get damaged. Okay, and once it's damaged, there is no recovery. Okay, you can't use it after that. Okay, so please be very careful. The soldering alone, again, if you are not confident, get somebody who is good in it to help you out. All right, and get your soldered pins all ready. All right, so that's the only thing you need to be very careful about, okay, in preparing the board. Okay, the rest of it I think should be fine. It's just a soldering, you need to be very careful. Okay. Yep. So I think that's about it. All that I have. Okay, and just the last reminder is again coming back to the Luminous grouping over here to make sure that you figure out, talk to your friends, talk to your teammates, who you want to partner with. Okay, and once you come to agreement, go and register. Okay, I'll be sending out links for 2 Google Forms later. One is for those who are stuck overseas or on stay home notice or things like that, and you're unable to come for classes for the labs. The second one is for those who are unable to form project teams. All right, and then I will see how I can group you all together. Okay, so that is all I have for you today. So thank you very much. Usually from last semester, what I've seen is in most cases I tend to overshoot a bit. All right, so if I go on till 12 or 12:05, 12:10, if you have other classes, okay, that you need to go to, please just log off and carry on. Okay, and then you can just look at the video for the last part, okay, to see what was covered or what was discussed. All right, so if in future some of the classes run until 12 or run a bit more, it's okay, you can just and log off from this class and carry on to whichever class you need to go to. Okay, so that's all I have. Any questions you have, you can ask me or you can put in the chat. If not, thank you very much, and I will see you all next Wednesday for the next set of lecture. Okay, so looks like no other questions. So thank you very much. Okay, so like I mentioned, I will see you all next Wednesday for the next lecture. Okay, and then I will brief you all more. Okay, thank you. Bye.